Hi everyone, I will talk about LEOCraft. I'm sure that you are aware of low Earth orbit satellites beaming high-speed internet connectivity from space. Most dominating player in this new landscape is Starlink, with 7,000 plus satellites already in orbit offering internet service in 100 plus countries, now entering Indian market too. Their long-term objective is to deploy 30,000 plus satellites with inter-satellite laser links, creating a mesh network in space to provide seamless high-speed connectivity anywhere in the world. Other players, OneWeb with 600 plus satellites focusing on commercial sector mostly, while Amazon Project Kuiper at the phase of testing having a plan to deploy 3,000 plus satellites too. So this current scenario forecasting a competitive space-based internet service market in future likely to carry a significant segment of today's internet traffic. So it is a legitimate time to ask, how do we design such network? What are the subtle crux of designing a highly optimized LEO network? Well, to answer that, we first need to address two major challenges. First, given a particular design, how do we evaluate the performance of that constellation? Okay, there are few simulation and emulation platforms have been developed over last few years, and each comes with its own limitation. The most recent one is Zeoverse, built upon Mininet platform, and it is not open source, so we couldn't able to test it. Next, we have Starrynet, which is partially available. It uses Docker containers to emulate satellites and ground stations, so the scalability is quite limited. Lastly, Hypatia is built upon NS3 platform, thus performance is constrained by NS3 and it do not include atmospheric attenuation in ground to satellite links. And most importantly, none of those work actually considered measuring the entire constellation performance while traffic flowing across all the ground station over shared satellite links. Therefore, we need a tool that can evaluate the constellation performance as fast as possible and should scale seamlessly. It should allow us the flexibility to quickly implement new design ideas with few lines of code, and it should also provide us flexibility to plug and play different optimization technique to test with it. And it should also include a interactive visualization framework that could render the topological changes, so we could correlate the performance traces to get an intuitive understanding of those networks. So we address all of those with LEOCraft framework. LEOCraft measures constellations, throughput, coverage, latency, end-to-end hop counts, and many more matrices with such fewer lines of code. The visualization framework of LEOCraft can render evolution of network topology changes at the granularity of nanosecond. LEOCraft is fast because it operates at flow level and it computes network measurement from intuitive model of LEO constellation. Those formulation of modeling is briefly discussed in the paper. Given the time constraint, I will mostly focus on throughput and coverage metrics. Now, at the implementation level, unlike previous work, we do not treat a constellation as a monolithic block, because inside a constellation, computing a coverage area of one satellite has nothing to do with the computation of others. Similarly, computing the route between a pair of ground stations completely independent of other pair of ground stations. So we exploit this and treat every component of these such networks like satellite and ground station as an independent block with the strict data exchange APIs. In LEOCraft, a module LEO Constellation Builder creates a top-level instance of LEO Constellation consists of all network components like satellite and ground station and add that instance into the LEO Constellation Simulator task queue. And this simulation framework executes all those simulations in parallel. And this parallelism is at functional level, distribute the function call uniformly across all the available CPU. and this approach scales seamlessly with minimum slowdown. Well, with that, a LEO constellation design problem can be formulated as follows. Given a bunch of ground station location and the traffic demand matrix across them, we are supposed to decide upon right combination of design parameters and a ISL topology that maximize the network performance. Alright, we have LEOCraft, then what exactly is stopping us to do so? Well, this is a high dimensional search space where each variable here denoting number of choices we could have along each dimension. Evaluating each choices will take certain amount of time based on the number of satellites and number of ground station in a constellation. Even if we assume each evaluation will take constant couple of minutes, a naive approach, let's say brute force or grid search approach, will take years to complete. Well, then how do we approach? What if we first figure out how the choices of those parameters actually changes the network performance? Then we could use that knowledge as an heuristic to trim down the search space and optimize new constellation design faster. So now let's look at those parameters. What are those parameters and how changing those parameters impacts the network performance? So first, altitude. In a constellation, satellites will maintain a particular altitude h. Without touching anything, if I increase the altitude, the coverage of a satellite will slightly increase. So the figure in the left side shows the performance impact of altitude using Starlink constellation, where the x-axis is altitude, y-axis showing you the performance metrics, where this blue dashed line is showing you the performance metrics, and this black dotted line at the bottom is number of ground station is out of coverage, and this red line showing you the throughput. So notice the coverage of the constellation increases with altitude. This higher coverage gives better path diversity to the ground station. Due to this path diversity, throughput increases up to a certain point. Because if we keep increasing the altitude with same exact transmission power and same transmission hardware, atmospheric loss start dominating and the result in throughput drops. So in summary, 5 to 10 kilometer change in altitude doesn't make much difference, but we should be mindful about our communication hardware's capability. Next, we have inclination angle. It's a bit similar to our altitude. Changing the value of E is like regulating the coverage area of the satellite. As you could notice in this three figure right side, how reducing the value of E increases the coverage footprint of satellite and the constellation. Therefore, on the left side, now x-axis is our elevation angle. So notice lower value of E increases the coverage area, and this gives a better path diversity to the ground station and the throughput increases. But even going towards the very lower value of E is like allowing ground to satellite link over the horizon, and such link first comes with enormous path loss and the throughput falls. Also, such links are not practical unless we put our ground station and user terminal at very high altitude to avoid all the obstacle. So in conclusion, altitudes and elevation need to be balanced for the desired objective of performance. Now, inclination. All the orbit in a constellation will have a particular tilt angle which is measured respect to the Earth's equator. Notice the performance traces from 0 degree to 90 degree. The performance matrix is exactly symmetric with 90 to 180 degree. Because any inclination between 0 to 90 degree is like a mirror reflection of any inclination in 90 to 180 degree. So let's focus on the first half. And notice if the inclination is closer to 0 degree, it means movement of the satellite is squeezed towards the equator. Of course, that leaves all the ground station at higher latitude out of coverage and throughput falls. On the other hand, 90 degree of inclination also reduces the throughput, because now satellites are moving above the polar region and there exists no major city and the ground station. In the middle, at close to the 40 degree of inclination, it gives maximum coverage and maximum throughput as the movement of the satellite restricted exactly above the population center. Now, in a constellation, given a budget or number of satellite, it's always arranged in a number of orbit O, number of satellite per orbit N. And these are two examples. We could, of course, have many such choices. Then, phase offset P is the relative positioning of satellite between two consecutive orbit. Now, these three parameters O, N and P are the most trickier because changing in the values of those parameters mostly tweaks the topological structure and that barely changes the coverage. But the throughput outcome of an topological structure depends on the other parameters as well. So those are dependent parameters. After deeply exploring this high dimensional search space, we found when the other parameters like inclination, elevation and altitude are close to the optimal value, any larger value of O means orbit at higher phase offset gives higher throughput. As you could see the same in this figure, in the where x-axis is the phase offset and y-axis is the throughput, and each line representing the different value of O. Notice any larger value of O at higher phase offset giving better throughput. But why? That is where LEOCraft visualization framework come into play. Notice in this globe, a shortest path from one side to the another side of the Earth always goes through intra-orbital ISL. So having more orbit closer to each other gives multiple parallel equidistance route, just like a multi-lane highway, accommodating more traffic without compromising upon other routes. And we validated those findings with different size of constellation against different 4 different traffic matrices, and the performance characteristics remain consistent. Now we use that awareness of the performance characteristics to trim the search space. So first we classify those parameters into two groups. Group 1 that impacts the coverage of the constellation, and group 2 that do not impact the coverage of constellation, rather tweaks the topological structure. Now in the group 2, from the knowledge of performance characteristics, we could directly set those values. So the search space is reduced to the group 1. Again, we could use further domain knowledge to reduce the search space further. For example, altitudes comes under the regulation on FCC and ITU, so we are not going to get much flexibility on that. Inclination, again because of that symmetric behavior, and we also know that those extreme value doesn't help in good result, so we could restrict it between 30 to 90 degree. And elevation angle is also dependent on the communication capability, but in our case we have restricted in between 10 to 60 degree. Then we use those 4 optimization techniques: simulated annealing, adaptive particle swarm optimization, differential evolution, and variable neighborhood search to optimize different size of constellation for given traffic matrix and ground station locations. Now here this solid line is showing the optimization time it took for the different constellation to optimize for our given traffic matrices and the ground station location without heuristics, and this dashed line in the bottom is showing the same optimization technique when used with domain knowledge and search space heuristics, and all the optimization technique improved at least twice, and variable neighborhood search outperforming all the others. Finally, those modern constellation goes one step ahead with multiple layers called shelled. Now in this figure I am showing Amazon Project Kuiper multi-shell proposed design, and each shell with different color for visual clarity. So in this talk I only discuss single shell design because each shell are independent of each other. However, LEOCraft can evaluate multi-shell design too. In our paper we have analysis of multi-shell design as well, and we also explored the ideas like introducing inter-shell connectivity between those shells. So if you are interested, please have a look into the paper. So in conclusion, designing a constellation is utterly complex task. To address that, we have been building LEOCraft, a modular framework. Because of this modularity, it is really now easy to extend that and implement new ideas with fewer lines of code to test new design choices. Our source code is publicly available in GitHub. A future work in this direction should include topology and trajectory joint optimization to address multiple objectives like throughput, coverage, and latency. With that, thanks for listening, and I am ready to take questions.